Welcome once again into the class of number theory. In the previous video, we have proved a theorem, that is phi mn is equal to phi m phi n. That means Euler's tangent function is multiplicative function. So I'm going to continue right from there. The next theorem is Euler's theorem. It is Euler's theorem, and the statement of the Euler's theorem is, if GCD of A and M is 1, then A raised to the power phi m is congruent to 1 modulo m. Where what is phi m? You know it very well, that phi is the Euler's tangent function, and phi m means the number of natural numbers less than m which are co-prime to m. So here is the statement of the Euler's theorem, that if A and m have GCD 1, then A raised to the power phi m is congruent to 1 modulo m. And how to prove the theorem? The proof is not difficult, it's really very easy. So first of all, what we will do, we will take a RRS system modulo m, and then we will create another reduced residue system modulo m, and from there we will move on to the on to proving this result. So let R1, R2, R3 and so on R phi m be a reduced residue system modulo m. Why the last one I have taken as R phi m? Because the total members of the reduced residue system modulo m is phi m, as per the definition of the Euler's function phi. So this is let this set be A. Let us denote this set by A. Now we will show that, we claim that this set B, consisting of the members AR1, AR2, AR3 and so on AR phi m. That means I have multiplied each member of the set A, this capital A, by small a, and constructed the new set, namely B. And I am claiming that the set B is also a reduced residue system modulo m. That I am going to prove. For this, what I will have to prove? We will have to prove three things once again. First, we will show that each member of the set B is co-prime to M. That means AR1 and M are having GCD 1, AR2 and M are having GCD 1, AR3 and M are having GCD 1 and so on. In general, you can say that ARI and M have GCD 1. This is the first thing what we will prove. Secondly, we will show that no two members of this set are congruent to each other modulo m. That means we will show that ARI cannot be congruent to ARJ modulo m if Ri and Rj are members of the set A. Ri and Rj are the member of A, that means ARI and ARJ are the members of B. This is the second thing what we will prove. And thirdly, we will show that for every x belonging to the set of integers, there exists some ARI in this set B such that this x is congruent to ARI modulo m. That means every integer is congruent to some member of the set B modulo m. So these three things we will prove, and by proving these three results, it will be clear that B is a reduced residue system modulo m. So these three we are going to prove now. For the first one, we are given that GCD of A and M is 1. We are given that GCD of A and M is 1. And since this set capital A, this is a reduced residue system modulo M, each member of the set A will be co-prime to M. That means you can say GCD of Ri and M is 1 for every Ri belonging to the set A, because A is already a reduced residue system modulo M. Now, if A and M are having GCD 1, Ri and M are having GCD 1, this directly implies that A, Ri and M will have GCD 1. Such results we have already proved in previous videos. So the first result is proved that each member of the set B is co-prime to M. Second result, we have to show that no two members of the set B are congruent to each other modulo M, and we will prove it by the method of contradiction. First, we will suppose that there are two members of the set B which are co-prime, which are not co-prime, which are congruent to each other modulo M, and then we will arrive at some contradiction. So suppose ARI is congruent to ARJ modulo M for some ARI and ARJ belonging to B. Suppose there are two members in the set B which are congruent to each other modulo M, which should not be. So we will arrive at some contradiction. And this means M divides ARI minus ARJ from congruence to divisibility, and A you can take out common. So this means M divides A Ri minus Rj. Now GCD of A and M is given to be 1, and we know that if A divides BC and GCD of A and B is 1, then directly it means that A divides C. So this result I am going to apply here. M divides A times this number, and GCD of M and A is 1. That directly means that M divides the other number. So what we will get from here that M divides Ri minus Rj, and this means Ri is congruent to Rj modulo M, and this is a contradiction because Ri and Rj are already members of a reduced residue system modulo M, and no two members of a reduced residue system modulo M can be congruent to each other modulo M. So we arrive at some contradiction. And why this contradiction? Because we have supposed that two members of the set B are congruent to each other modulo M. So it is not possible. That means no two members of the set B are congruent to each other modulo M. And finally we will show that for every integer x, there is a member in the set B such that the two are congruent to each other modulo M. So for the third part, let x be a positive integer such that GCD of x and M is 1. Already we are given that GCD of A and M is 1. And if GCD of A and M is 1, we know that there will be a linear combination of A and M which will be equal to 1. So definitely there will exist integers B and Y such that AB plus MY is equal to 1. From here we will take two results. First is that what is the value of AB is 1 minus MY. And secondly, B and M, a linear combination of B and M is equal to 1 because A and Y are integers. So that means a linear combination of B and M is equal to 1, which gives that GCD of B and M is 1. Which gives that GCD of B and M is 1. Already GCD of x and m is 1. And now GCD of b and m is 1. So from these two, you can conclude that GCD of bx and m is equal to 1. So GCD of bx and m is 1, and this A is a set of reduced residue system modulo m. So definitely if bx is co-prime to m, then bx will be congruent to at least one member of this set. So that means there exists some Ri in the set A such that this bx is now congruent to Ri modulo m. And now multiply this congruence both sides by A. So what you are going to get is that ABX is congruent to ARI modulo m. And this AB, the value of AB is now 1 minus my. So it is 1 minus my x is congruent to ARI modulo m, which you can rewrite as x is congruent to ARI plus m times xy modulo m. And if you have seen my previous videos, you must know that if there is a congruence relation modulo m, then from this congruence equation modulo m, any multiple of m can be removed. So here you are having a multiple of m. It is a congruence equation modulo m, and one of the terms is a multiple of m, so this can be removed. The equation will still be okay. So x is congruent to ARI modulo m, and that is what we wanted, because we have taken x co-prime to m, and from the set B we have obtained one member which is congruent to x now modulo m, and this makes the set B a reduced residue system modulo m. Now look at, there is already a reduced residue system A, and now we have shown that B consisting of AR1, AR2, AR3, AR5M, this is also a reduced residue system modulo m. So now we are having two reduced residue systems modulo m. Therefore, product of all these members is congruent to product of all these members modulo m. So what is the product of these members? So it is AR1 into AR2 into AR3 and so on, AR5M is congruent to, on the other side you are having R1, R2, R5M modulo m. The product of two different reduced residue systems modulo m is congruent to each other modulo m. On the left hand side, A multiplied by A multiplied by A multiplied by A, how many times? 5m times. So it will give you A power 5m. And take this term to the left hand side. R1, R2, R3, R5m is already here, the product. And the same product is now coming from the right hand side to the left hand side, so it can be taken out as common. Taking this product R1, R2 and so on, R5m as common, from this term you will be left with A power 5m and minus, because this term is coming to the left hand side, it will become minus, negative, it will change its sign. And R1, R2, R5m is already taken common, so you will get here 1. And what you will be left with? 0 on the right hand side, modulo m. And this means your m divides this R1, R2, R5m multiplied by A power 5m minus 1. Now GCD of m and R1 is 1, because R1 is a member of reduced residue system modulo m. GCD of m and R2 is by the same rule 1. GCD of m and R5m is 1. So GCD of m and this complete number is 1. So let it be A and let it be B, let it be C, and it is your A as M. What you are getting here, A divides BC. A divides BC. But GCD of A and B is 1. GCD of A and B is 1. And you know that if A divides BC and GCD of A and B is 1, then A divides C. So what you are going to get from here is that M divides A raised to the power pi M minus 1. And now this divisibility relation, if you write it in a congruence relation, what you are going to get? In a congruence equation, it will be converted to A raised to the power pi M is congruent to 1 modulo M, which was the required result to be proved. So we have proved the Euler's theorem. Now there is a note, there is an important corollary you can say of this theorem. What will happen if this M is a prime number? If M is a prime number P and P does not divide A. If M is a prime number which does not divide A, that means GCD of A and P is 1. This is already there. So what this result will be? This will be A raised to the power phi P is congruent to 1 modulo P. But what is phi P? For a prime number, suppose you take prime number 7. What will be the value of phi 7? The number of natural numbers less than 7 co-prime to 7. Every natural number less than 7 is co-prime to 7. GCD of 1 and 7 is 1, GCD of 2 and 7 is 1, GCD of 3 and 7 is 1, GCD of 4 and 7 is 1, GCD of 5 and 7 is 1, GCD of 6 and 7 is 1. That means your phi 7 is equal to 6. That means 7 minus 1. Or in general you can say phi P is equal to P minus 1. So this phi P is equal to P minus 1. So your result will become A raised to the power P minus 1 is congruent to 1 modulo P. But for this result you must have P to be a prime number that does not divide A. And if you multiply the congruence equation both sides by A, multiply by A, so what you will get? A raised to the power P minus 1 into A will become A power P. On the right hand side you will get A. So A power P is congruent to A modulo P. These results, that means A raised to the power P minus 1 is congruent to 1 modulo P. This result is sometimes known as Fermat-Little theorem. So it is Fermat-Little theorem, and this is another result obtained from Fermat-Little theorem. These two results are true when P is a prime number that does not divide A. But interestingly, this result is also true if P divides A. That part I am leaving to you as an exercise. And now I am moving on to another important theorem, or you can say important result. And after that, in the next video, I will move on to the Chinese remainder theorem, that means linear congruences and systems of linear congruences in the next video. But here, one more theorem I am going to take, and this theorem is, you can take it as a theorem, you can take it as a result, because it is not a fundamental theorem. You can say it is a consequence of Fermat-Little theorem, or you can say Euler's theorem. If P, Q are distinct primes, if P, Q are distinct primes such that A raised to the power P is congruent to A modulo Q and A raised to the power Q is congruent to A modulo P, then A raised to the power PQ is congruent to A modulo PQ. You can take it as a corollary of Fermat-Little theorem or corollary of Euler's theorem. You can take it as an independent result. So to prove this, we will use in fact Euler's theorem or Fermat-Little theorem. So how to prove it? Proof is not very difficult. It is in fact very easy. P P and Q are distinct primes. So first of all, you will get A raised to the power Q is congruent to A modulo Q, and A raised to the power P is congruent to A modulo P by using that Euler's theorem. Now you can replace this A by any power of A, because if Q does not divide A, that means Q does not divide any power of A. So replace this A in the first equation by A raised to the power P. Replace A by A raised to the power P. So what you will get? A raised to the power P power Q. So it will become A raised to the power PQ. So A raised to the power PQ is congruent to P modulo Q. Now look at this result and then look at this result which is given. A raised to the power PQ is congruent to A power P modulo Q, and A raised to the power P is congruent to A modulo Q. And using transitivity, you can directly say that A raised to the power PQ is congruent to A modulo Q. So A raised to the power PQ is congruent to A modulo Q. The same game I am going to play with this equation. Replace A by now A raised to the power Q here. So the left hand side will once again become A raised to the power PQ. So A raised to the power PQ now is congruent to A power Q modulo P, and A power Q is congruent to A modulo P. Once again, using transitivity, you will get A raised to the power PQ is congruent to A modulo P. A power PQ is congruent to A modulo Q, and A power PQ is congruent to A modulo P, and P and Q are distinct primes. So if P divides APQ minus A and Q divides APQ minus A, then their product PQ will also divide A raised to the power PQ minus A. That means A raised to the power PQ is congruent to A modulo PQ. And this was the required result to be proved. So here I am going to stop this video. In the next video, we'll move on to the linear congruences, Chinese remainder theorem, and many more topics. Till then, thank you. Thank you once again.